Hey, y'all.
Hello.
Yep.
Good morning.
Greetings and salutations. I'm going to share my screen with y'all. And can you all see that? Get a show of hands.
I can.
Yes.
Okay, perfect. Okay, so let's get started because we have a big day today. I want to make some announcements. Then I've had some questions on bee trees, so I want to go over quickly some notes about insertion and deletion in bee trees, things that you should really be focused on when you're doing it. Then I also will go over extendable hashing so that you can finish the homework. And finally, we're going to start getting into our last subject on databases, which is NoSQL databases with an emphasis on MongoDB, which is perhaps the most. So first, let's get started with the announcements. So we have a midterm coming up next week on Thursday, the 18th. And if you go to the course website, you'll see this link toward the bottom called exams. If you follow that link, you will see that there's a midterm review guide that goes over the material that I think you need to review for the exam. And so just go through that, make sure that you're familiar with it. And it goes through everything, even up through the NoSQL stuff that we haven't covered yet, but will. And then there's a sample midterm with solutions. And I will tell you that the sample midterm is a little heavier on the multiple choice, multiple answer than the exam I have prepared is. And that's in part because Canvas is so picky about its multi-answer questions and basically counts off for incorrect answers, which I didn't necessarily want. What I like to do with my multi-answer questions is say, there's like 3 correct answers, and then you choose the 3 you think are correct. And if you get 2 out of 3, I give you 2 out of 3 points, but Canvas doesn't do that. So there's somewhat fewer, there's actually only a couple multiple choice, multiple answer. I think there's 3, whereas the more common ones are write a query. So toward the end, you see things like write a query and or write something in the relational calculus. Now, 465 students, I'll tell you right now, you'll also be writing a relational calculus query. Found that actually the undergrads do better on the relational calculus than the relational algebra. You can definitely, there'll be an entity relationship design picture. There will be one on either B plus trees or extendable hashing, like the sample problem. The one big difference is on normalization, the sample exam just gives you the functional dependencies for one problem. Here it is. It says assume that the table has the following functional dependencies. So I do that for one problem and give you the functional dependencies and ask you to do the decomposition. But on another problem, I actually say derive the functional dependencies for me. So that's different than the, that's a problem that's different than the sample midterm. Okay, but the sample midterm otherwise gives you a good idea. The one thing it doesn't have is MongoDB on it. I can tell you that what I will probably do with MongoDB is either have some, and NoSQLs have a couple of questions, multiple choice, multiple answer testing your material, knowledge of the material, and some queries in MongoDB where I'll give you some tuples and ask you which tuples would be returned by different MongoDB queries. So I won't ask you to write a MongoDB query, but I will ask you to be able to recognize which tuples will be returned by one. The exam will be open note, open book. It will be done using the Respondus lockdown browser, and I know many of you don't like it, but I have strong reasons for using it. Last spring, when I used it, I had no cheating cases, and when I didn't use it, I had multiple cheating cases. And not only does that irritate me, it's not fair to those of you who don't cheat. So the only way really that I can think of to ensure fairness is to use the lockdown browser. To those of you who dislike it, my apologies, but it's the way it is.
By lockdown browser, what do you mean exactly? Like we can't click off the browser or something?
Yes, so the lockdown browser, so I will post so what I'm going to do, let me so the lockdown browser essentially disables everything on your laptop except for Zoom. And so you can't have other applications open. You can't click off to other pages except for the links I give you. So it basically freezes your screen so that you can only take the test. And I will post some directions to the startup, to the page. You'll have to download the software for it. It's relatively simple.
But if we use the Respondus lockdown browser, then how are we going to be able to look at our notes and stuff?
So I can provide links that allow you to go to the notes. So it gives you the ability, I can give you domain names, like the domain name for the Xi book, the domain name for my notes, and then you can click around and in those things. It's very good. So if you try to click on a link that takes you outside the domain, it blocks it doesn't do it. It comes up with a little message saying link blocked. But if you're still in the domain, like the utk.edu/BV domain, you're fine. So you can click away all through my notes, through the homework. Same thing with the Xi book. You can click to wherever you want. Now, it doesn't work with Canvas. So if you want to have the homework solutions available, you need to print them out. And if you, open note, open book is, remember, normally the only thing you would have available is the book, which I will make available to you. You would have to print out everything else. So it's kind of actually convenient in this case to have a computer, but I suggest you still kind of come up with a short crib sheet of your own, just because you can lose a lot of time trying to look things up the day of the exam on the computer. But you'll see all this on Thursday, because I'm going to prepare a sample Respondus lockdown quiz that we will do on Thursday in class. So I will, later today, I will post again the link to the OIT site where you can download the software for the lockdown browser and get started with it. Basically, I want to say, sorry. So on Thursday, the practice quiz is just going to have you walk through a few things that you'll need to be familiar with for the exam next Thursday. So for example, how to get access to the palette of special characters for relational algebra or relational calculus, so that you can quickly put down those symbols on the exam. With ER diagrams, how I'd like you to create them using ASCII art if you decide not to draw it. And then finally, you will have the opportunity on a couple of the problems to draw a picture of the solution. You'll then have to take a photo of it with your phone or your iPad or your tablet and upload it to Canvas after the exam is done, because while the exam is in progress, you can't upload anything. So all of those things you'll get practice with on Thursday in class. Please try to make it on Thursday, just because that will give you some practice with what you need to do. So questions about any of this? I know I went over a fair amount.
Yeah, so I just went to the OIT link for Respondus, and it says my device is not supported because I'm on Linux. And I also don't have enough space to dual boot Windows.
Okay, we can take that offline and talk about it, okay? Send me some email.
All
I
right.
have solutions for that. Other questions? Okay, so if there's no other questions about the exam, then another thing that is changing is going forward, there's going to be much less after class quizzes, which I know some of you will be happy about, and more in the way of doing challenge activities. So it's like, I'm going to check chat. Does someone have a question on chat? Nope. Okay. So if you go to Canvas, you'll see starting today, after class March 9th, JSON and nosql. So starting today and essentially going forward, there are almost no quizzes anymore. Instead, what you'll be doing is challenge activities from the book. So I'll be careful to tell you when a quiz is coming up, but today, what you'll be doing is some activities with JSON and nosql after class, and they're going to be book activities. So there's no quiz today. Thursday, there's neither a quiz nor is there a after class activity. So just so you know, for Thursday, there's no quiz or after class activity. But today there is. So make sure that you are aware of this transition. Okay. Go ahead.
I see that there's some deadlines, like that one that you're pointing on says 11:30.
Don't worry about the other ones. I have to push those deadlines. So I only am ever a couple weeks ahead. So that after class March 3rd, we haven't gotten to it. This deadline will get pushed. So don't worry about any of these. They'll all get pushed to the appropriate times.
Okay, but they'll always be due like at the beginning of a class. I see
Yes.
one that's like 12:30 instead of 11:30.
Yeah, because that was
Okay.
the last time I offered this course. It was a slightly different time.
Okay, gotcha.
The only one that's up to date right now is this one. Actually, none of these should be published. I don't know why these are published, to be honest. So I will unpublish them. The only one you should be seeing is this one. And in fact, I just saw I hadn't published the module. Oh, great. That's what happened. Okay, I'll have to. The only thing you should be seeing is this one. So I have to. It may not have even been visible because the module hadn't been published. So now it should be visible.
Yeah, you couldn't
Yeah, it
click on them,
wasn't.
but I was wondering.
Yep. So now if you refresh your Canvas page, you should be able to see it. Okay. Other questions?
Yep, that looks good. Thank you.
Okay. Perfect. Okay. Also, I am probably not going to be lecturing as much going forward. I still will, but there's going to be more interactive kind of in-class activities, and that's actually going to happen starting Thursday as well. Not only will we be doing this quiz, practice kind of quiz in class on Thursday, but on Thursday, rather than lecture a lot about MongoDB, I have a nice, I think, handout that you can walk through and interactively copy and paste and experiment with MongoDB, kind of like a tutorial. And I think having you do it hands-on is often better than just listening passively to me. So in the second half of the course, when we get into web programming, you're going to find that I don't always lecture as much, and sometimes I have you do in-class activities, or I focus more on stuff that's related to the web projects. So it gets a little more, I guess, interactive, and you become more active participants. Okay, so next what I wanted to do was just go through a couple things with the B-tree visualizations. So I've been having some questions, one of which is when you have a leaf that is going to split and it's going to have an odd number of children in one, I say move it to the left. And what I want, here I'm going to insert 700, which is going to overflow this leaf. What I want, when I say put it in the left leaf, what I mean is one of the two leaves is going to be odd. Right now, L is equal to 4. So this is going to split the leaf. And as you see, whoops, they put it into the right. But I believe I told you to put it into the left on the homework. Let me take a look and make sure about that.
It's in parentheses at the end there.
Okay, it says I told you to copy the extra tuple to the left node. Yes. So what I want is, so the visualization, I kind of intentionally did it so you couldn't just lazily do it. So the visualization is putting the extra key in the right leaf. I want you to put the extra key in the left leaf. So this, in my homework, I'd want 700 to go over here. Okay. Another thing that I'm going to go back now, skip back, because I want to show something else. So when you insert into a leaf, like I say 700, so in this case, 700 is going to become the first key in the new right leaf. And you're going to see that 700 gets, quote, copied up to the parent. But you'll notice it also stays in the leaf. So this is a common mistake I see on both the exam and the homework, is that students promote 700 to the parent, but they don't also leave it in the leaf. So a key can appear in both a leaf and in a parent node. Now, the reason this confusion comes up is because if you split a parent node, then in fact, the key will get promoted rather than stay in both the current node and the parent. So what I'm going to do now is switch to a much smaller tree to make this clear what I'm talking about. So I want to be able to split things more easily. Okay, so in fact that showed it, so I'm going to skip back. Okay, so right now, if I insert, say, 500 into this tree or leaf, it's going to split it. And you'll see that 500, so you'll see it went just too fast. So I'm going to skip back. I'm going to do some drawing. Okay, so I'm going to insert it got too big. There we go. Okay. Okay, so I'm going to insert 500. Yeah, let's change that format to black. So when I do it, I'm going to get a split. Okay, and the way it's doing the split is putting the odd tuple on the right. Okay, so when it does that, it copies 400 up to the parent. And whoops, I shouldn't have it there. In fact, the line, new line would come down here. So 400, as you can see, is both in the leaf and it gets copied to the parent. Now the parent is also at this point too big. It has 4 children, so it has to split. And 2 children will go to the right parent, 2 children will go to the left parent. So basically, this will happen and this will happen, and then 300 gets promoted to be the new root. And I think this is what causes students issues, is because in the leaf, 400 both stayed in the leaf and was copied up to the parent. But when an interior node splits, then if promotion occurs like 300, 300 actually in that case disappears from the interior node and literally is promoted. So it's kind of like there's 2 separate cases. If it's the leaf splitting, then the key both stays in the leaf and gets copied up to the parent. But if it's an interior node that's splitting, then the key when it's promoted disappears from the interior node. Okay, so hopefully that's clear. I'll show you now I'll let it run. And I think I might be, nope, I'm not stuck. Might be stuck. There we go. So I will insert 500 just to show you that it all plays out the way I claimed it did. Whoops, that's a delete. So see, it all played out the way I said it would. So are there questions about that? Anyone have a question there? That's one thing you need. That's several gotchas that you need to be careful about. Okay. So in that
I just have one quick,
Mhm.
like not this example, but the one you were talking about before, where everything should move to the left, I guess. In this example, that 400 down at the bottom in the leaf should be over there with the 300, according to your scheme, right?
Correct. Yes, you got it.
Okay.
Perfect.
Okay.
You got it. Other questions? Okay. So the next issue comes with delete. So I'm going to need to add a few more things here before I'm going to be able to do my delete. Insert 250. Okay. So first thing is, let's say I want to delete 300 here. Okay, one thing is you can borrow from a neighbor if that neighbor has enough space to give you one. In fact, they'll never have enough here, so I need to increase my degree. So let me go to degree 4 because now L is equal to 3 and do a bunch of inserts. Delete 400, I don't want that twice. Still don't have enough, sorry. Need to get up a big enough tree. Okay, almost there. A few more inserts. Actually, I might have it now. Yep, I have it. Okay. So let's say I want to delete 850 from this node right here. So the first thing you want to do is see if you can borrow a leaf from a left or right sibling. And this diagram makes it look like this. So the diagram, whoops. The diagram makes it look like this node right here. So I'm deleting 850, okay? I'm taking it out. So it looks like I can borrow a val or key from its so-called left neighbor, but it's not a neighbor, it's not a left sibling. You can only borrow from either a left or a right sibling, which means that you have to have a common parent. Okay, this node right here does not have a common parent with this node. Okay, so if I call this A and I call this B, A's parent is 900, B's parent is 350 and 600. So this leaf is not in the running for borrowing a node, because despite this very misleading arrow, which I hate in this visualization, it is not a left sibling, it is not a neighbor to this block A. Block A, the only thing it can adopt from is this right-hand sibling. And because this right sibling is already at its minimum, you're going to have to, in fact, merge rather than being able to borrow anything. So when I delete 850, I'm going to actually have to merge this entire block. Okay. And I did have a question on the about, okay, what happens if I have multiple choices with my, about what to choose, whether to choose the left or right. So I'm going to add a couple more things here. I'm going to add 20. Oops, tried to delete 20. Insert 20. Okay, so here's a case where, let's say I want to delete 400. Now I can actually either borrow from my left because it has enough, or from my right. And for the homework, I said you should borrow or merge with left sibling if possible. So in this case, I can borrow from either my left or my right, and I want you to borrow from the left. So I would want you to move 100 over to here when you delete 400. Okay, and when you do that, you would end up adjusting that key, because now 100 would be the smallest key in that node. So questions about deletion and how you borrow or merge?
Actually, I got a question about are we always going to stay left? And what I mean by that is, when we split, the extra node goes in the left side, or when we promote, say we need to promote, but there's an even number of keys in the node, do we pick the leftmost
Yes.
of the middle?
You pick the, yeah, so if you're promoting, so let's say you're in an interior node like this, and you have 40, 50, 80, and 100, and you have to promote, you would promote 50 because it's the leftmost of the two.
Okay, I just wanted to make sure that we were
Yep.
staying consistent with the
Yep.
left.
I'm
Pick
going
the
to try
left
to stay
always.
consistent with everything. It'll always be left. Anytime you
Okay,
have
cool.
a choice, you do left. That consistency is everything. I'm Mr. Consistency. So everything, anytime you have to make a choice, it's left. Okay. Other questions? Okay.
I have a question.
Mhm.
So if you couldn't borrow from the left neighbor, you borrow from the right neighbor?
Correct. So
Okay.
if for some, let's see if I can, if there's another second, let me clear this. So let's say that 100 wasn't in here. So I'm going to get rid of 100. Okay, so now if I delete 400, I would have to borrow from the right. I'd borrow 600 because I can't borrow from the left anymore. Does that make
Okay,
sense?
and then you would you delete 600. I mean, not delete. You remove 600 from the interior node and make it to be 700.
Exactly. So if I deleted 400, 600 would now be borrowed. Because 600 is now no longer in this node, 700 becomes the smallest value in this leaf, and this value would be updated to 700. That's exactly right.
Okay, and you couldn't, if you couldn't borrow from left and right node, you merge on the left.
That's your first, yes, your first choice is to merge on the left if that's available to you. And if that's not possible, then you would merge on the right.
Oh, okay, I see.
So here's an example. Let's say that I deleted 800 from here. I can't, it's the leftmost sibling. It has no left sibling, so it's impossible to merge it to the left. It can only merge to the right in this case, as an example.
Okay, that makes sense. Thank you.
You're welcome.
I
Other
had
questions?
another, yeah, I had another clarification. So when you said, could you clear the writing?
Yes.
So if you wanted to put, like, say you're inserting 600 and you said put the extra tuple into the left side. So you're inserting 600 to like the 350, 400, and 600. Would that 600 parent node be 700 then?
Okay, just a second. So I'm doing an insert now,
Yeah, you're doing
and I'm
insert.
inserting another 600. Is that what you want me to do?
Yeah, so would you put that extra, you clarified that you wanted to put it on the left side, right?
So in this case, the 600, right, so the 600 would come in. And now with inserts, you don't borrow. In this case, you have to split.
Right.
So you'd have two 600s in the same, in one leaf, and 700 and 750 in the other. So the, yeah, so at that point, 700 would come up here and it would point down to this one.
Okay.
Here, I can show you, I'll run it. So I'll insert 600. And I can somehow, there we go, move it. Comes down. Oh, that's not where it should be inserting. That's another bug. Oh my gosh. Well, that's a bug. because anything, you can't have this situation. It's anything less than 600 is supposed to go here, and anything greater than or equal to 600 is supposed to go there. So that didn't work
Right.
out so well. Let me put another, let's put 605 in. So it splits and 700 goes up. I'm not going to make you do duplicate tuples ever, okay? Because
Okay,
it does
okay.
get a little bit confusing when you have duplicate tuples, and I don't want to get confusing like that. So I will not have you work with duplicate tuples.
Okay, gotcha. Thank you.
You're welcome. Okay, I need to actually move on at this point. I need to get to extendable hashing, and I need to at least say a few words about NoSQL. So if you have further questions, I will be available after class for a few minutes. And I also have office hours today. So you should be able to also get me in office hours. Okay, so extendable hashing is essentially a scheme so with B plus trees, we can't guarantee a constant number of block accesses. With B plus trees, there's always this log factor of log m divided by 2, and then n divided by L divided by 2. So as n grows larger, then it's not constant. While it grows very slowly, the number of block accesses is not constant. With extendable hashing, what we're going to be able to do is limit us to a maximum of 3 block accesses, period. So basically the insight behind extendable hashing was, can we create a tree that is never in effect more than 3 levels deep? And the answer is yes. So it's a generalization of normal hashing. So with separate, and it's a generalization of separate chaining. So you may remember with hashing, you have buckets and they point to values that hash to that. So actually 25 probably doesn't hash to that because it is, actually it would. So anything that hashes to a bucket goes to that bucket. And that doesn't work really well for secondary storage because these buckets can get arbitrarily big. So for example, if a bucket ends up with, say, 2,000 keys in it, that might require too many block accesses. So if each block, for example, could only hold 400 keys, then the bucket would need 5 blocks for 2,000 keys. So that's no good. The problem with just separate chaining is you have a fixed sized table and the blocks could get too big. So the obvious solution is resize the table to ensure that no bucket contains, or to ensure that a bucket requires only 1 block to store its keys. So that will guarantee, so if this is the main table, that's one disk access. Then it points to a bucket or a block that contains keys. That's access number 2. And then each of them point to a tuple, which is access number 3. So the hash table itself is a 2-level index. The main table is the first level, the bucket is the second level, and then the keys in the bucket point to the actual tuple. So you limit yourself to 3 block accesses, provided that you can ensure that every bucket requires only 1 block to store its keys. And the way we do that is we hash the keys into bits. Okay, so for convenience, I'm just going to use 4 bits. So let's say that, so something like this, say. So you hash the key into a bit string. So in practice, there's 32 or 64 bit strings, but for purposes of illustration, I'm going to limit myself to 4-bit bit strings. And initially, you just insert into the top level. So I'm going to assume that I can hold, I'm going to say 4 keys. So I'm going to say M equals 4 keys per block. So initially, let's say I insert these 4. I'm good. This is I just have 1 block. It's the top level. Now when I insert the next key, let's say it's 0001, I'm going to have to split. And what I do in this case is I double the size of the hash table, because this is the hash table at this point, just 1 bucket. And now it's too big, so I have to split it. So I'm going to split it into 2 based on the first bit. So the first bit is going to be either 0 or 1. So all zeros will go into one bucket, and all ones will go into their bucket. Okay, and the duplicates are fine because you can have 2 keys hashed to the same value. So it doesn't mean they're the same key. Just with hashing, you can have 2 keys hashed to the same value. So now in the main table, I indicate that I have 2 entries, one that points to anything that starts with a 0 and the other that points to anything that starts with a 1. So now I continue, and let's say I do a few more insertions and I get 1101, and I want to insert now 1011. So again, it's going to go into here, but it's going to overflow the bucket, so I have to split it in 2. So now I'm going to consider the first 2 bits in order to do my splitting. So the 1 zeros will in effect stay in this one. So I'll add 1011. And what I'm going to do is move the ones that start with 11 will get moved. So 1100 moves, and the other 1100 moves, and this 1101 moves. Okay, so that's gone, that's gone, that's gone. Okay, but I have a problem, which is I have 3 buckets, and as you can see, I can't have only 2 entries. So what I have to do is, again, double the hash table. And now it's going to consist of 4 entries based on 2 bits. Now, the 0, 0 and the 0, 1 are still going to point to the same bucket, because for 0, anything that's leading with the 0 still can fit into that bucket. Whereas the other 2, I have to consider both bits, and so they stay separated. They point to separate buckets. Okay? So to handle this situation, what we do is in each bucket, we indicate how many leading bits that bucket represents. So here, this one is still only requiring 1 leading bit, whereas the other 2 require 2 leading bits. So the idea is, if we split a bucket that is, and this directory is also using 2 bits. So we say capital D equal 2 to be that the main table is using 2 bits. We say lowercase d to indicate that the bucket it's only using 1 bit. Lowercase d equals 2, it's using 2 bits. Lowercase d equals 2, it's using 2 bits, leading bits. Okay, so if we need, so now we can keep adding. If we need to add a 0, 1, 1, 1, you can see we go to 0, 1, and we'll put it into here. And we can add yet another one. So let's add 0, 0, 1, 0. So it gets added. And now let's add 0, 1, 1, 1. That's going to force a split. But because this d equals 1 is less than this capital D equals 2, we're not going to have to double the size of the directory. Instead, we can simply split this node so that the 0, 0s go into one bucket and the 0, 1s go into the other bucket. So I just inserted 0, 1, 1, 1. So what's going to happen, I'm going to create a second bucket. I'm going to move all the 0, 1s to that second bucket. And all the 0, 0s will stay in the original bucket. And I'll move this pointer so it now points to here, and we update the D's so that they're now both equal to 2. Okay, so that's the basic idea, is when necessary, you split a bucket just like you would in a B+ tree. And you kind of have 2 cases. If little d is less than capital D, you split the bucket and move half the pointers in the main table to the new bucket. Okay, so that's case 1. Case 2, if D is equal to D, then you have to double the size of the main table. And for the most part, in the main table, you'll now have double pointers to most buckets and single pointers. So most buckets now have at least 2 pointers, maybe more, and only the new bucket, only the split buckets have single pointers to them. So that's the idea. So in order for it to work, there is a critical requirement, and that is that the main table be stored contiguously. So the main table must be stored on contiguous blocks. There's no scattering. It must be stored on contiguous blocks so that it's like an array. And the reason for that is that the reason you're using those leading bits is you can convert those leading bits into an index. So for example, if the table is of size 4, it's really 0, 1, 2, 3. Notice 0, 0 is 0, 0, 1 is 1, 1, 0 maps to 2, 1, 1 maps to 3. So what you're doing when you are inserting a key like 1, 0, 1, 1, you look at the first 2 bits and you translate it to an integer index. And then you need to be able to jump directly to the right block, which you can only do if it's stored on contiguous blocks in secondary storage, because you're just going to do a computation. If you know that, for example, there's 400 keys per block, and you know the index is, for example, 805, then it's going 805 divided by 400 is equal to 2. You're going to map to block 2. And you'll jump directly there to get it. So that's one big restriction on extendable hash tables. The main table has to be stored in a contiguous block. So every time you double it, you have to find enough secondary storage free that you can store it all as a contiguous block. That's not a requirement for the buckets, but it is a requirement for the main table. Okay.
So it can take multiple blocks, right? Though, as long as they're contiguous.
Pardon?
So it can take multiple blocks, right?
Yeah.
As long as they're contiguous.
As long as they're contiguous. And
Okay.
in practice, it will. It will require multiple contiguous blocks.
Okay.
Okay. Other questions? I'm not going to hold you responsible for deletes, only for inserts. So we're not going to worry about how we delete from a extendable hash table. Okay.
Actually, quick question, hopefully quick. So far, it looks like we're just talking about the first 2 bits. How is just look at the first 2 determine? I guess as the main table grows, you start increasing the number of leading bits that you look at for the main table.
So for example, this table now is it's some sense it's fully loaded. Any bucket that now splits is going to force me to double the size of the table to 8. So then I would be considering the first 3 bits.
Okay, so we're basically just doing powers of 2. Every time you need to increase the main table, it goes to the next power of 2.
Exactly. So that's why you keep this
which adds another bit.
Yes, you just tack on one more bit, which effectively doubles.
Okay, makes sense. Thank you.
Yep. It was a very clever idea. The mathematical analysis is killer, but the idea itself is relatively simple. So the big question then is, in practice, does the main table blow up, become too big to represent contiguously? And it turns out it doesn't. It has some very sweet properties. So in practice, with a uniform hash function, meaning the hash function is good at uniformly distributing the keys, then the expected, the average leaf is natural log 2 equals 0.69 full on average. And that turns out, interestingly enough, to be the same as average leaf for B tree, B plus tree. That's kind of interesting. It makes sense because in both cases, you're splitting a bucket or leaf when it exceeds the size of M. So there is kind of some intuition as to why they're roughly equally full. And then the expected directory size, or the number of entries, is, it turns out, order n to the 1 plus 1 divided by m divided by m. So n equals number of tuples, m equals block size, essentially, for keys. So as long as m is pretty big, you can see that this exponential isn't going to grow very fast. It's going to be relatively close to linear as long as m is pretty big, which in practice it is. So that was the really good news when they started experimenting with extendable hashing in practice, is that the directory size really does not get to be too big, and therefore extendable hashing proved to be practical in the real world. As I said previously, MySQL only supports B plus trees. It doesn't support extendable hashing, but SQL, Oracle's SQL does support extendable hashing. And again, the big advantage of extendable hashing is it right here. You never have, you're guaranteed exactly 3 block accesses to get to a tuple. And in fact, in the real world, big portions of the main table get cached in memory. So in practice, it's often just 2 block accesses because big chunks of the main table are actually cached in main memory. Same thing for B plus trees, actually. Generally, the top few levels of a B plus tree can also be cached in memory. So that also reduces the number of actual block accesses for B plus trees. Okay, so questions about anything that I just covered. I know I went over it fairly rapidly, but I think it's not all that different from what I was doing with B plus trees. Okay. In that case, take a deep breath. So we're moving on, and we're going to be talking about a different kind of database called nosql DBs. And the book does a very nice job of explaining or motivating them. So I am not going to regurgitate the book. I'm just going to talk about a few things that I feel the book I didn't assign or that the book didn't talk about. So basically, there's 2 issues with relational DBs. So I'll say when you have what's called big data, the book did a good job of saying, well, it's generating much, much more data than a typical relational database handles. And that means that many know that with that much data, you need to do some kind of distributed database, and that's bad for relational databases. So relational databases tend to have to be shared memory. So the problem is locking is very complicated with relational databases. So disadvantages of relational they're not distributed. it's very difficult to do the locking, and I'll show why. So they're not distributed DBs, so they don't scale up well for huge data. And the other issue is that you have what is called semi-structured data. So the data isn't all, you don't have a fixed set of columns anymore. Instead, you have many, many columns, and many of them have nulls in them. So you often have what is called sparse data, where a lot of the columns have no values. Okay, so many columns, many potential columns are null. So a good example is that if you're aggregating data from different social media sites like Twitter, say Facebook, say Instagram, each of them might have a different structure for its data. And you're combining all of it into one big database for data analysis. So the problem is each of them is structured differently. So if you're representing a Twitter document or tuple, all the columns that Facebook and Instagram would use would be null. Same thing for Facebook. It's unlikely there'll be much overlap between the columns for Facebook and the ones for Twitter. They might be some, like name, but there's going to be a lot of attributes that are different. So again, there's going to be a lot of null values. So relational databases don't handle this situation very well either. In my notes, I gave another example for semi-structured data, and that was a payment method. So with a payment method, it could be cash. So for a payment, you might have cash, credit card, or check. And in each case, the attributes are going to be very different. Cash is easy. It's probably amount tendered and your change. For credit card, it's probably going to be the, so this is amount tendered. So for a credit card, you probably want the issuer of the credit card number, the expiration date, the security code, maybe the person's name. With a check, you're certainly going to want the check number. You're going to need the person's name, probably their account number, the bank. Normally you take down the driver's license number and the driver's license state. So these are all often mutually exclusive fields. So if you try to represent this in one row of a relational database, there's going to be a lot of null values for the unused payment methods. So this was the motivation for NoSQL databases. Now, the reason relational databases don't distribute well is because they enforce something called ACID in they do transaction processing. So relational databases are oriented toward what's called transaction processing. So they want to ensure that updates are consistently propagated and that there's not competition. So ACID stands for atomic, consistent, isolation, and durability. So atomic means that every query and transaction, so a transaction is equal to a number of queries. So atomicity, what it means is either all queries successfully execute or none of them execute. It's all or nothing. You can't have some subset of the queries execute and the remainder fail. If any one of the queries fails, the transaction fails. So they succeed or fail together. That's atomicity. Consistency means that you go from one consistent state of the database to another. So all constraints are always satisfied. So remember, there was entity integrity, referential integrity for foreign keys. It ensures that when you go from one state to another state, that all constraints are always satisfied. Isolation means that you don't have essentially race conditions. So you get the same result if two transactions are executed serially or in parallel. So that means if they conflict on something with a write, then they're going to have to be executed sequentially. So if two transactions, say A and B, both want to write the same tuple, then one of them has to be basically stopped, or you need locking. So you have to lock the relation to ensure that only one of the two gets access to that tuple, and then it releases the lock and the other transaction can access the tuple. So that's called isolation, and that's what really causes problems with distributed computation, because with distributed computation, you start to split the database across multiple processors and storage systems, and the locking becomes very difficult because now you have to start using messages to communicate the locks, and that just gets very complicated. And it turns out that relational databases, for the most part, don't try to do it. So they won't, they'll require a centralized file system. They won't allow for a distributed file system. So that's all down to isolation. And then durability is that if you commit a transaction, its results are always remembered, even if the database subsequently crashes. So once the transaction commits, durability means that if the database subsequently crashes, that the transaction is saved. Okay, so what's really slowing everything down is this isolation aspect. And so what many NoSQL databases do is they relax this isolation requirement, and they instead introduce something called eventual consistency. So they relax isolation, replace. So NoSQL databases often, DBs, often replace isolation with eventual consistency. Okay, so eventual consistency says that if you make a series of updates that, okay, let me just a second. I want to get the right definition. Okay, so eventual consistency says that you maintain multiple copies of data on different So multiple copies of data are held on different nodes. Of a cluster. Okay, and that could be a distributed cluster. Okay, so when an update occurs, okay, it's executed at multiple nodes concurrently. And is committed when a quorum of nodes have committed the update. Okay, and then it's completed at other nodes as well. So what this says is that given enough time, all nodes converge to the same update, hence eventual consistency. Okay, so given enough time, all nodes converge to the same update. But here's the rub. If there are two competing updates, so let's say that A and B both try to update. So let's say there's 10 nodes where it's copied. And you need a quorum of 6 to commit. So, or let's just say 5. So that there can't be any race conditions. So A and B try to change the same node. So they start out and A changes node 1 and B changes node 10. And now there's a race. Whichever one commits first on 5 nodes wins the race and their update commits, but the other one is lost. So one of the two will be lost. That's the problem with eventual consistency, is that when two updates are percolating at the same time, it becomes a race as to which one gets the quorum first. Whichever one gets the quorum first wins. So there's no deadlock. There will be eventual consistency. One of them will get the quorum and will be eventually propagated to all 10 nodes. But the problem is, we lose the other update, okay? Which is disastrous in many situations. Consider a bank that has financial transactions and it has multiple withdrawals on the same account. It absolutely cannot afford to drop any updates. That would be a disaster. It would probably go bankrupt if that happened, because it would be showing more money in the account than what there was. Let's say that the person had $500 in their account. Transaction A is for 400. Transaction B is for 300. As you can see, the combined transactions overwrite cause the account to go negative. Let's say though that only B gets propagated And so they still think there's $200 in the account, when in fact it's minus 200, but they'll still continue to think there's 200 in the account. They will still actually process more transactions against the account. So this eventual consistency only works when you are prepared to lose updates. Okay, which isn't always a bad issue in social media, but it's a horrible situation to have in things like financial transactions. So there are times when it is perfectly acceptable to relax the isolation condition. So remember, what we are doing is relaxing the isolation condition in ACID and replacing it with eventual consistency. And that's allowing us to distribute our computation across multiple multiple file systems. And that's getting us the speed that we need to do our massive processing. As for the semi-structured data, that is what the book did such a good job of covering. They went over the main kinds of NoSQL databases, which are key value, column-oriented, document-oriented, which is what MongoDB is, and graph-oriented. And the after-class activity for today has you go through and work with those. And I think the book did a nice job explaining it. So I'm going to just have you work through those after-class activities. The same thing with JSON. I will talk a bit about JSON on Thursday. And I'm also on Thursday going to talk a little bit about a theorem, couple of theorems about that basically say there's a trade-off between availability of your data and latency of how fast you can get it. So I'm sorry, there's a trade-off between latency and consistency that is also made between relational databases and NoSQL databases. They're called the CAP theorem and the PAKE-LC theorems, which I'll go over on Thursday. It's not part of what you have to do for the after-class activity, so don't worry about it. So we'll get to that on Thursday. As I said, I'm not going to cover key value, column, graph, databases in this class. We're going to cover the document-oriented one on Thursday when we talk about MongoDB. What I'm going to hold you responsible for, well, I'll tell you on Thursday what I'll hold you responsible for on the exam. I'm going to let you all go now. If you have questions about B+ trees or extendable hashing or something else, feel free to give me a holler. Otherwise, you're free to go, and I will see you on Thursday.